Hello everyone, I'm Palak Kumrawat, a sophomore studying at International Institute of Professional Studies, Devi Ahilya Vishwavidyalaya, Indore. This video is assignment of numerical analysis and design under the guidance of Dr. Shaligram Prajapat sir. We will be covering the solutions for first and second internal test, which consist of some numerical and algorithmic based questions, which consist of some true false and including MCQs too. So let's get started. In this question, we are supposed to write algorithm for the following given polynomial. We have to write both the approaches, that is recursive approach and brute force approach. And then we also have to design algorithm when we will be dividing the polynomial by x minus r and also for derivative of p of x and have to fill the cells in the table too. Algorithm for evaluating the polynomial using iterative approach, we have to read the values of x and an array for the coefficients of each term and the number of terms. And we will take an variable s and initialize it to 0, which will be storing the sum of all the terms. And for each term of the polynomial from highest to lowest degree, we will compute value of term, which can be calculated by multiplying the coefficient with x raised to the degree of the term, and then add the computed value to the sum variable s. And after evaluating the values of each term and adding it to the sum variable, we will return the value of s as the value of the polynomial. Column 1 is the algorithm for iterative approach, and the column 2 is for the recursive approach, which does the same as an iterative approach, has the same initial stages of iterative approach, that is reading the value of x, number of terms, and the coefficients of each term in array A, and initializing the variable sum to 0, and then reading the coefficients into the array A. And now at last the recursive function is called by passing the parameters as n, x and a of, that is array of coefficients. If the degree of the polynomial is 0, it will the polynomial function will return the value of constant term a of 0, which will be the first term. Otherwise, we will compute the value of polynomial recursively by computing the value of current term by multiplying the coefficient with x raised to the degree of the term and then adding the function called by passing parameters as n minus 1, x and array a. And at last we will be adding all the calculated values and it will be returned by the polynomial function. This is how the recursive function works. It will call itself again and again, and the results will be calculated on the basis of stack. The first in will come first out. The left column is the algorithm for dividing the polynomial by x minus r, and the other column represents the algorithm for computing the derivative of the polynomial. So these are the steps for writing the polynomial, which we have written in the next slide. So we will discuss how we have written the algorithm for both of the tasks. So the left side of the algorithm represents when we will be dividing the polynomial by x minus r. So here same, we will be reading the value of x, n, that is number of terms, a an array of coefficient, and r, which is the value we have to subtract from x. We have initialized some variable to 0 and q, that is a quotient variable, r, a remainder variable. Both have been initialized to 0. And from the highest to lowest degree, we will be computing the value of current term of coefficient, that is CQ, by dividing the coefficient by x minus r. So here a underscore I is, that is a of I, a of current term. And then we will add the computed value to the quotient polynomial Q, CR, which represents the current term of remainder, which can be calculated by multiplying the quotient of the current term with x minus r. And at last r, which is the remainder term, which we'll be getting by subtracting the computed value from the current term of the polynomial and adding the computed value to the remainder. And at last we will return the variables q, that is which represent quotient, and r, which represents remainder. Now the right column represents the algorithm for computing the derivative of polynomial, in which we have done the same initial steps which we are doing till now. Here we have taken another new variable d, which will be storing the value of derivative calculated for each term. From highest to lowest degree, we will compute the value of derivative of the current term by multiplying the coefficient with the degree of the current term and subtracting 1 from the degree. And then we will add the computed value to the derivative polynomial d. And at last, the results are in the variable d, which we will be returning. In this question, we have to draw the flowchart for the following task and complete the table. So we have to draw the flowchart for subtraction, multiplication, and division. And by using the flowchart, we will compute the values for the given data sets, and wherever we have come through the error messages, we have also mentioned that. So now let's discuss the flowchart, which will be very helpful in filling the table cells. So this is the flowchart for subtraction. Make a note that the flowchart for subtraction and addition both is same. So here we will be reading the input as both of the numbers n1 and n2 with separated values of mantissa and exponent. Then we will check the exponential part of both the numbers. If the exponential part is equal, we will be adding the mantissas of the number and check whether the obtained number is normalized or not. A normalized number just means that the part before the decimal number is 0 and part after the decimal number is a non-zero number. So if it's normalized, we will print the numbers, and if it's not, we will be normalizing and then check if the exponent part is greater than 99, then we will print overflow, and if it's not, we will check whether the exponent part is less than minus 99. If it's yes, we will print underflow, and if it's no, we will be going back to A and then check again whether it's normalized or not. If it's normalized, we will be printing the values, and if it's not, we will normalize it again. So this will be a repeated process after adding the mantissas. And if the exponential parts are not equal, then we will check which of them will be having the greater exponents. The one having the greater exponents, we will be shifting the mantissas of the smaller exponent by the difference of both the exponent values. That is, if the E1 is greater than E2, yes, then we will be shifting the mantissa of E2 by the difference of E1 minus E2. Positive, we will be taking the positive values, and then we will be adding the mantissa of M1 and M2, and exponent will be of E1. And then we will check whether the number is normalized. We will be printing the value, otherwise we will normalize it. So in this way, the flowchart for the subtraction is being designed. This is the flowchart for multiplication, for which we will be reading the numbers n1 and n2 with both the mantissa and exponential part separately, and then directly multiply the mantissas of both numbers and add the exponents of both numbers. And the obtained number will be checked whether it is normalized or not. If it is normalized, we will print the number with separated values of mantissa and exponents. And if it's not normalized, we will be normalizing and check. After normalizing, we will check whether the exponent is greater than 99. If it's true, we will print overflow. Otherwise, we will check for the underflow condition, that is if exponent is less than minus 99. If it's true, that is an underflow condition. Otherwise, we will again check the number for the normalized number or not. So in this way, the flowchart of multiplication is designed, and we will be calculating the values of the data set by using this flowchart. The process for dividing two numbers is same as in the case of multiplication and subtraction, that is taking numbers as input with separated values of mantissas and exponents, and then we will be dividing the greater mantissa with the smaller one, and the difference of the exponential values will be stored in an exponent variable, which should be a positive number, and then check whether the obtained number is normalized or not. If it's not normalized, we will be normalizing it and then check for the overflow and underflow conditions. If it's normalized, we will be directly printing the numbers. So this is the flowchart for the division of any numbers uh, in the computer. We have to verify the given expressions, that is associative and distributive laws for the following given values with the fitting four mantissa digits, and we have to write the results accordingly. We will be verifying by substituting the given values in the expression. So first, we will be calculating the value of a plus b for addition, subtraction, multiplication, division, whatever type of mathematical operation we are doing, we have to follow proper algorithm which we have designed in the previous questions. We cannot directly evaluate the values as we do in the mathematics. We have to check for the normalization condition and the underflow, overflow, everything we have to consider here. So the in the case 1, both the LHS value and the RHS value are not equal, as you can see in the paperwork which I have done here. So the associative law doesn't hold for these values, and in the case 2 also, both the LHS and RHS values are not equal according to the given expression. So no law holds for these values. Hence, we cannot provide a correct answer without the truncation of digits. Now, let's move on to the true-false section. We have to state whether the written statement is true or false. So, let's move on to the first statement, which states that we minimize the number of arithmetic operations whenever possible. So, this statement is true because there are several reasons why it is beneficial, as in case of efficiency, accuracy, robustness, memory usage. So considering all these factors, this statement can be considered as true. Performing arithmetic operations is computationally expensive process. So by minimizing the number of operations, we can improve the efficiency, and which also reduces the processing time. Each arithmetic operation introduces a certain degree of error, which can accumulate over multiple operations. By minimizing the number of operations, we can reduce the overall error and improve the accuracy of the results. Arithmetic operations can also lead to numerical instability and divergence, especially when dealing with large or small values. So we can reduce the risk of numerical instability and make the algorithm more robust. Each arithmetic operation requires storage space in the memory. By decreasing the number of operations, we can reduce the memory usage and optimize the use of available resources. So considering all these factors, this statement is true. Second statement states that avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of problem. If it cannot be avoided, then take the difference before doing other operations. So this statement is true because taking the difference of nearly two equal numbers can lead to loss of accuracy and numerical instability, especially when dealing with floating point arithmetic, as the difference will be a very small number and that may be lost due to limited precision of floating point arithmetic. Just in the case of example, the value of C will be very small, and due to the limited precision of floating point arithmetic, this can lead to inaccurate results and numerical instability, especially if C is used in further calculations. So to avoid this, it is recommended to use alternate formulation of problem, which avoids taking the difference of the two nearly equal numbers. This can be algebraic manipulation or reordering of the calculation to reduce the sensitivity to small changes in the input. So the third statement is adding or subtracting numbers starting with the smallest number and works with numbers in ascending order. So this statement is true as adding or subtracting numbers with different magnitude. It is important to start with the smallest number, which reduces the impact of limited precision of floating point arithmetic because small numbers have fewer digits and are less sensitive to rounding errors than the larger numbers. So by working with numbers in ascending order, we can reduce the accumulation of rounding errors and numerical instability. As in the example we have taken, adding numbers, small numbers first reduces the impact of rounding errors and improves the accuracies of the result. So this statement is true. So the fourth statement states that do not formulate an algorithm that tests whether a floating point number equals to 0. So this statement is also true as it is not recommended to formulate an algorithm that tests whether a floating point number is equal to 0, as floating point numbers are not exact and their values may subject to rounding errors. Due to the limited precision of floating point arithmetic, it is difficult to represent certain numbers exactly, including 0. This means that even if two floating point numbers are mathematically equal to 0, their representation in the memory may differ due to rounding errors. So instead of testing whether a floating point number is equals to 0, it is better to use a threshold or a tolerance value to check whether the absolute value of the numbers is sufficiently small. So this approach of checking the number to its absolute value is whether it's small or not is called epsilon test. So it is better to check whether the number is satisfying the epsilon test or not rather than checking its equality with 0. So using an epsilon test, we can handle floating point numbers more accurately and robustly than testing for equality with 0. Fifth statement is Hill conditioning of problems is normally due to improper formulation and can be eliminated by carefully reformulating the problem. A practical way, if detect suspected ill conditioning, is to alter the parameters by small amounts and observe their effect on the solution. So this statement is considered to be partially true because ill conditioning of proper can be due to improper formulation, but it can also be due to the nature of problem itself. Ill conditioning means the small changes in the input or the parameters of the problem can lead to large changes in the output of the solution. This makes the problem difficult to solve accurately and can lead to numerical instability. So one way to detect suspected ill conditioning is doing sensitivity analysis, that is by changing the values of input by small numbers, and if the solution is highly sensitive to small changes in the input, then the problem is likely to be ill conditioned. However, simply altering the parameters by small amount may not always be enough to eliminate ill conditioning. In some cases, a careful reformulation of problem may be necessary to improve its conditioning. This can be changing the formulation of problem or introducing additional constraints or assumptions. So while detecting suspected ill conditioning through sensitivity analysis is a useful first step, but it cannot work always. We need sometimes to reformulate the problem. So this statement is partially true. Statement is after a numerical algorithm is obtained, check if can it can lead to numerical instability. In such algorithms, error grows in each step of calculation. In such case, reformulate the solution procedure to get a stable numerical algorithm. So it is indeed, it can indeed lead to numerical instability where error grow in each step of calculation. This can be due to variety of factors such as ill-conditioned problem, numerical round-off errors, or instability in the algorithm itself. So to ensure numerical stability, it is important to carefully analyze the algorithm and its implementations to identify potential sources of instability. If numerical instability is detected, then the solution procedure may need to be reformulated to get a stable numerical algorithm. This may involve using alternative numerical methods or algorithms that are known to be more stable, modifying the existing algorithm to reduce the impact of numerical errors or round off, or introducing additional constraints or assumptions to improve the conditioning of the problem. So therefore, this is partially true statement. Statement is after a numerical algorithm is obtained, check if can it can statement is if a lot of rounding errors and subsequent loss of significant digits is anticipated, and if no alternate formulation to avoid this is possible, then carry more significant digits in the critical calculation using floating point numbers in double precision mode. In this mode, the length of mantissa is twice that of other floating point quantities. So this statement is true because particularly when dealing with quantities that vary widely in magnitude or when performing operations on values that are close to the limit of machine precision, in such cases, if no alternate formulation is possible to avoid this loss of precision, carrying more significant digits is in critical calculation can help to minimize the impact of rounding errors. One way to achieve this is by using floating point numbers in double precision mode, which allows for twice the number of digits in the mantissa as compared to standard floating point numbers. This can help to increase precision of critical calculations and reduce the potential for rounding errors that may affect the accuracy of the final results. However, it is also important to note that increasing the precision of calculation can also increase the computational cost. and memory requirements of the algorithm. So it is important to balance all the factors that the machine computations may be affected. The eighth statement is double precision requires large memory space and slow down calculation. This statement can be considered as partially true because yes, double precision requires more memory space than standard single precision, as each double precision floating point number requires 64 bits, that is, of memory compared to 32 bit of single precision mode. However, whether or not double precision slowdowns calculation depends on the specific context and computational requirement of the algorithm. So in some cases, double precision may be necessary to achieve the desired level of accuracy or to avoid numerical instability caused by rounding errors. So in these situations, the benefits of increased precision may outweigh the additional memory requirements and computational costs. In other cases where lower precision is sufficient or where the computational resources available are limited, it may be more efficient to use single precision floating point numbers. So ultimately, the choice of precision for numerical algorithm should be based on careful consideration of the trade-offs between accuracy, computational efficiency, and memory requirements, taking, taking into account the specific context and goals of the problem being solved. In the third iteration of finding square root of 5 with starting point 7 using Newton-Raphson method, relative error is 0.0013. So based on the information given, we can make guesses, assuming that the formula used to find the square root of 5 is zero point 0.5 into x underscore n plus 5 by x underscore n, where x underscore n is the representation for the nth approximation and x underscore n plus 1 is the representation for n plus 1th approximation. So we can estimate the value of x underscore 3 iteration as follows. So the relative error after solving all the steps of the computation is 2.24119. So it is not equal to 0.0013. So therefore the third approximation for square root of 5 using Newton-Raphson method with a starting point of 7 and a relative error of 0.0013 is approximately 2.24119. So this statement is false. The 10th statement states that the iterative methods are compared on the following parameters: rate of convergence, amount of computational efforts per iteration, sensitivity of the methods to the starting value and the intermediate value. So this statement is absolutely true. The iterative methods are compared on the basis of following parameters only. The rate of convergence refers to how quickly the iterative method converges to the desired solution. The faster the rate of conversion, the better is the method. And the amount of computational effort per iteration refers to the amount of computations required to obtain the next approximation in the iterative process. It is a method that requires less computational efforts per iteration is preferred more. And sensitivity of method to the starting value and the intermediate values refers to how sensitive the method is to the initial guess and intermediate values used in the iterative process. A method that is less sensitive to the initial guess and the intermediate value is preferred more. So this statement is true.